mic on? My mic is on. Hey, I'm streaming. I'm gonna give it a minute and see if more people want to show up to watch this live because I just turned it on. In general, I'm gonna try and remember to write BRB on the screen for things where I'm not actively teaching, so that if you are watching this video later, you can sort of figure out where to jump past. You don't have to watch until the BRB goes away. I'll be back in a minute. Hey, I'm back. I'm back, but my stylus isn't working so great. I got this way fancier new computer recently that made me give up my old tablet that had a really good stylus and everything. Well, I didn't think it was really good, but you know, it worked. My fancy new one doesn't work, or the stylus is just garbage. I have to change the battery constantly on it, or I'm not sure what it is. It might be one of these batteries I'm using isn't as good as the other. It sometimes feels that way. But yeah, I'm switching this battery out right now. How's it going? You're in Cal 2. This is a great course. This is a hard course. The old battery's charging, the new battery's in, the new battery's working right away. That's a good sign. We're on 142, day 1. DAY 1. 1. Hey, you're in Cal 2. I guess before I start teaching calculus, let me talk a little bit about what Cal 2 is. In Cal 1, you're likely to be given a problem that says differentiate x e to the 3x, and you use the product rule. The derivative of x is 1 times leave the second part alone, plus leave the first part alone times the derivative of e to the 3x times the derivative that inside the e to the is 3, and then maybe you clean that up a little and your answer is e to the 3x plus 3x e to the 3x. Cal 1, you learn the product rule, you're able to take derivatives. In Cal 2, it's not so much that you do the product rule differently, but instead of you writing this part, you're likely to write differentiating x e to the 3x with the product rule gives the derivative of x e to the 3x is e to the 3x plus 3x e to the 3x, period. What's the difference? The difference is at the end of Cal 2, you're speaking in sentences, where at the end of Cal 1, you're sort of just showing your work. You're moving from a place where you are showing off your ability to do your computation. You're moving from presenting computations as your answer to presenting thoughts and thought structures and arguments, and this leads to this leads to this. You're speaking in sentences instead of speaking in baby talk. I have kids. If you've had kids, you've sort of seen them progress from barely putting the words together to putting together sequences of thoughts, and it's a big difference, and it's sort of hard to acknowledge it. If you look at your what's it called? The list of classes that they offer at your school. I don't know what school you go to. Hey, you're in USCL right now. A lot of the summers, we get people from Clemson and Columbia, or from USCL. We get people from all over who are home for the summer taking a class. I don't know what your home school is. But whatever it is, probably if you look at the list of courses, there's a whole bunch of them that say the prerequisite is Cal 2. You have to have gotten through Cal 2 to take linear algebra or abstract algebra or there's a ton of different classes for which it says you need 142. Abstract algebra doesn't need you to know integrating by parts, which is one of the things you're going to learn here. There's no particular piece of Cal 2 that you need to know in order to take an abstract algebra or a linear algebra, or there's a few things for some of them. But the real prerequisite is you need to be a person who speaks in sentences instead of a person who speaks in baby talk. And this is largely where we're headed with this class. So just to let you know, that's kind of what's going on in Cal 2. We're going to have 3 exams. This class is going to run for 6 weeks, so we'll aim to have an exam about every other week. Exam 1 is going to cover techniques of integration. You should know what an integral is. And you should be able to integrate some simple functions right now from the end of Cal 1. You're going to learn a bunch more. That's going to be 1 exam's worth of stuff. Exam 2. Oh, and the exam 1 is very likely to be, hey, here's a bunch of functions, integrate them all. Exam 2 is going to be sequences and series. There's some introductory stuff about definitions and what they mean, but a large part of it is going to be, I'm going to give you infinitely many numbers to try to add up. You're not going to try and say what they add up to. That turns out to be a very difficult problem. The key thing that you want to be able to answer for this exam is, do they add up to a finite amount or do they add up to infinity? This is the main difference you want to try and isolate in Cal 2. And that's going to be the bulk of what exam 2 is. And we're going to have exam 3, which is basically other. We're going to talk about polar coordinates. We're going to talk about volumes of revolution. What else is in there? Oh, approximating integrals. These are the 3 parts of the exam. The course description says that this class has a Maple Lab attached to it. I don't have a Maple Lab to take you to, so coronavirus seems like as good an excuse as any to skip that part, which I think that part is usually good for people's grades because it's the easy part, but it's also just a huge hassle. If you had this class at Columbia or Lancaster and had a Maple Lab, you know, it kind of just sucks. But I'm kind of happy to have an excuse to skip it. Yeah, let's start doing some math. Hey, if you're watching this live, send me a text just so I know what I'm saying is going through. That seems like the easy way to. I'd like to be able to answer questions to people who are watching live. I don't have a good way to watch the YouTube chat channel. Cool. Let's talk about integration. Let me talk about a couple things. Homework. I've got a big homework set posted. I think it's all the homework problems for the year. Hey, someone's here. So now you know how long the delay is. The homework's posted. It looks like. Do I have it open? I don't have it open. Let me go into my Blackboard. Do I have Blackboard open? This is the wrong class. This is the right class. Hey, here's what the homework looks like. Instead of putting homework problems, like saying what book to get the homework from, I don't want to make you all buy the same book because there's a good chance you have all different calculus books because you took Cal 1 at different schools maybe. So I just wrote up a bunch of homework problems. Today we're probably going to get through 1 through 13. Actually, I'm not sure how far we're going. Oh no, 1 through 4 are substitution. 5 through 13 are parts. I don't know. I'll let you know at the end of class. To turn in your homework, I want you to take a picture of it. Oh, don't show that. Take a picture of it, text it to me, or don't text it to me. I'm going to give you an email address to send the homework into. It'll be due on exam day, but I wouldn't wait until exam day to start doing the homework. If you, so I've taught long enough to know that I need to assign homework, or like I need to make you do the homework and make you turn it in, or nobody will do the homework and things go badly. But I still haven't learned that enough to the point where I actually care about the homework. So I'm not grading it directly. It's not due till the exam day. If you have questions about the homework, feel free to text me, hey, I don't know how to do this problem. Maybe take a picture of the work that you've done. Texting is a really good method for communicating math stuff because you can write out, hey, I did these 3 lines of work. Can you see what the mistake is? Like it's pretty good to do that. Like writing an email that says, hey, when I differentiated this, I got this, and then that sucks, but taking a picture and texting it is decent. I will soon set up a group text if you're comfortable texting that information to everybody. It's nice to be able to see what other people are working on. Hey, I got 2 people watching. Hooray! It's nice to see what other people are doing. I want to try and recreate the good parts of that classroom experience, but if you don't want to text other people your hard times with the homework, I understand that. I know people who don't like asking questions in class either. That's fine. But there's going to be a group text. You can ask me questions there or privately. Either of those is fine. If you're watching, you can text me right now. Some people are texting me now. I will try and keep an eye on my phone to see when people are interrupting me with questions. I mean, I don't mean interrupting in a bad way there. Feel free to interrupt me with questions. That's what it's for. So homework, it'll be due at the time of the exam. You'll email it to me. Don't email it to me at my school email address. I will put what the email address to send it to is on Blackboard. I'm not going to write down what it is right now because I feel like it might be a dumb idea to put my email address on YouTube. I don't. Maybe that's not something I need to worry about, but I'm not doing it. The exams are going to be similar. I want to put the exams all on the same day. When it gets closer to exam day time and when I actually know all the students have contacted me, I'll be asking what's a good time. I'm hoping Fridays at 2 o'clock. Are you free Fridays at 2? If you're not, well, I mean, let's not try and work that out right now. I'll text you about that. But hopefully everybody can take an exam Friday 2 to 4. I want everyone taking them at the same time. I'll tell you more about the exam when the exam is closer. We got a little while before we need to think too hard about that. Homework and exams are basically going to be it for the course. Do the homework, do the exams. If you have questions on the homework, text me. The exams you will also take pictures of and email to me. You might want to, I guess the homework is good. Make sure you know how to send me an email of a picture from your phone easily, because like the timing of you need to be able to send me your exam as soon as you're done. So make sure you get the hang of that when you send me your email, and make sure you send me your email before the exam. The final will be based on all the exams. I'll say more stuff about about the exam when we get closer. Anything else to say? I printed off some lecture notes. I use this, what is this, Windows Journal. I use this to take notes on every year, and the thing I do is I print off last year's notes and use them as this year's, so they get a little bit better every time. These printed in a weird order. Okay, so start going bottom up. Okay, I don't know why I did that. I'm printing 6 slides on a page, and they're going on a weird order. You don't need to care about that. Let's start with some thoughts on substitution. Say you should have seen integration by substitution in Cal 1. If I hand you the integral of e to the x cosine of e to the x. Come on. Dx. This is an obvious choice candidate for integration by substitution. The obvious u to pick, your you generally want to be something that you see on the inside, whose derivative you kind of see on the outside. Here I have an e to the x on the inside, and the derivative of that is also e to the x is exactly on the outside. There's no kinda about it. So I can write u equals e to the x. Du is e to the x dx. I'm kind of a stickler for making sure you get the dx there because it helps you keep track of if you're doing the substitution correctly. Then you want to be able to rewrite the integral. This is cosine of u, and then e to the x dx combine forces to become du is e to the x times dx. My goal is to write the exact same thing as before with nothing extra and nothing missing. In the end, I want to have a problem that's only about u and not about x. And then hopefully I want to do that problem. Now I want to integrate cosine. My problem has no x's left, so I'm allowed to actually do the integral. Some teachers say you're not allowed to write an integral with mixed x's and u's. I'm not one of those teachers. I think that's fine as long as you don't actually try to integrate something that has both the x's and u's combined in it. Like, what do I mean? That is not a very clear explanation. What I mean is sometimes people will say, I need to make this change. Dx, they'll take this and solve for dx. Dx is du over e to the x. And then they'll start doing substitutions. This is the integral of e to the x is u, cosine e to the x is cosine u, dx is du over e to the x. This is kind of an illegal thing to write because I have u's and x's mixed. I have x's. Mixing x's and u's is bad. Some teachers will say you are not allowed to write this. I think it's okay to write this as long as you don't actually try to integrate it. There is a good reason to not write this that we'll see in a second where it matters more. But in the end, you do something like, okay, I'll turn this u back into an e to the x, cosine u du over e to the x. And the e to the x's cancel, and okay, now I have just u's. Integral of cosine u du. Okay, now it's safe to integrate. And so now we're actually allowed to integrate it. What's the integral of cosine? The thing whose derivative is cosine is sine. The integral of cosine u du is sine u plus c equals sine of what was u? U was e to the x. I got the hiccups. And that's the correct answer to this problem. Whether you're allowed to write this in the middle is something you can argue about. A thing I want you to have in mind as you're doing this, I like explaining integration by substitution as doing French math problems. If someone gives you a French algebra problem, how do you solve a French algebra problem? Step 1 is you translate the problem into English. That's what all this step is. I'm taking my X problem, which is hard, in some sense because it's written in a different language. I'm using a conversion rule to convert it from French to English. Then I'm doing the problem in English. Then I'm translating my answer back into French. To get the French answer to a French problem, when you don't speak French, the thing you are likely to do is translate to English, do the problem in English, translate the answer back into French. Those last two steps are the steps people forget about. A lot of people will get to cosine u and they'll put a box around that. They'll change it into cosine u to the x or something. You actually have to do an integral at some point. The problem was about doing an integral. At some point you're going to do that integral, and then translating your answer back is about the fact that the problem they gave you was about the letter x. So your answer should be about the letter x for them to work out right. Right? Okay. So there's a basic example of a substitution problem. If I have the integral of come on, stylus. Do I need to change batteries back? How is this? There we go. If I have the integral of x squared e to the 5x cubed. I'm assuming you can do a problem like this from Cal 1, but I want to show you the way I write this out because I think there's some value to it. What's a good choice of u to use here? I'm going to want u to be a thing I see inside whose derivative I kind of see outside. I see a 5x cubed inside that e to the. And I think to myself, what's the derivative of 5x cubed? The derivative of 5x cubed is 15x squared. And I basically see 15x squared here. I see the x squared part. I don't see the 15, but that's just a constant. I can fix the constant. So I'm going to write u equals 5x cubed. That thought bubble stuff was me convincing myself this is a good idea to try for the u. If u is 5x squared, then du is, what's the derivative of that? It's 15x squared dx. What does this mean? This kind of doesn't mean anything. The thing to write is that du dx equals 15x squared. And then you pretend you can move the dx to the other side, and it doesn't actually make sense, but it's the thing that makes the chain rule backwards work in an integral by substitution. The way I like to do this is to say, okay, I wish I had 15x squared dx. Some people will tell you to divide both sides by 15, and that works, and that's fine. Here's the way I like to do it that has less writing involved, and I think is worth it because of that, is I see the dx, and I see the x squared. I wish I saw a 15. Well, I'll just stick a 15 there. I'm allowed to stick a 15 as long as I cancel it. I like smushing in a 15 on the inside and smushing out a 1/15 on the outside. I'm allowed to do that. 15 divided by 15 cancels. 15 is a constant, so moving the 1/15 outside of the integral is legal. This to me is a way of making an integral by substitution happen smoothly when it might not have happened smoothly otherwise. I get 1/15 integral of what? This and this and this join forces Voltron style and become du. Du is all those three things. E to the 5x cubed, I can call that u. Hey, I have it all in u's and not x's all in one go. I like this push in a 15, pop out a 1/15. I think it's good. Keep in mind, you can only pop out a thing that is a constant. If it was an x, then I would want to leave the 1/15 inside there. I think I need to switch my battery back. I wonder if maybe this thing says that the battery's charged. This must be the bad battery. Maybe the other battery's the good one. I hope this isn't what the whole class is going to be like, is me constantly changing batteries. Damn it. What's the integral of e to the u? What's the integral of e to the x is maybe the better way to phrase it, and then just write your answer about a u instead. It's 1/15 e to the u plus c. What's the integral of that? And now I've done the integral, now I need to translate the integral back to English. 1/15 e to the 5x cubed plus c. Cool. That's my push in a constant, pop out a constant trick. I don't know if you saw this in Cal 1, but you should think how substitution works on a definite integral. What's a definite integral? That's an integral where you have the little numbers, the bounds of integration. If I have the integral from 3 to 4 of x squared over x cubed minus 8. This is a good problem due to the substitution on, but I have these bounds of integration there. Why is this different? The thing to keep in mind is a definite integral, your answer is going to be a number. It's going to be 5.68, whatever. That's not the actual answer, but it's a number that has digits that you can write down. A number that has digits is the same in French and English. So this whole philosophy that we were talking about of take your French math problem, convert it to French, do the integral, and then convert your answer, like the whole translating back thing. When your answer is a number, you shouldn't need to translate a number. There's two ways to do a definite integral by substitution. Option 1, the dumb way, is to just hide the numbers. And then at the end, once you have your whole answer, plug in those numbers. I want to do this substitution. My u choice is x cubed minus 8. du is the derivative of that is 3x squared. I wish I had a 3. I'll put in a 3 and pop out a 1/3. This turns into 1/3 integral of that stuff is all du. That thing on bottom of the fraction is u. There's nothing left on top. What's the integral of 1 over u? It's natural log absolute value of u plus c. What was u? U was x cubed minus 8 plus c. So now I have my answer. So, having done this little side problem that didn't have the digits there, I should now be able to answer the problem that has the digits there. There's my mouse. So, the integral from 3 to 4 of x squared over x cubed minus 8 dx is going to be that answer evaluated from 3 to 4. The answer was 1/3 natural log absolute value x cubed minus 8 close absolute value. I need to evaluate that from 3 to 4. Hey, heads up. The times are changing. More and more people are writing this as a bracket, 3 to 4. When I took calculus, they used a bar instead of a bracket, so I'm finding it hard for me to change, but that is what the bar is for. It may have been a bracket in your class. I need to evaluate that from 3 to 4, so it's 1/3 natural log absolute value 4 cubed minus 8 minus 1/3 natural log absolute value 3 cubed minus 8. 4 cubed is 64. 64 minus 8 is 56. Absolute value 56 is 56. Minus 1/3 natural log absolute value 27 minus 8 is 19. If your absolute value of 19 is 19. If you're feeling really fancy, you can take this is 1/3 natural log of this minus this. The rule is natural log. Subtracting the logs is dividing inside the log. So this is natural log of 56 over 19. Okay, here's a pretty compact way of writing the answer. If you left it like this, that's fine. You can get digits on it either way. That's the dumb way of doing it, where you do the entire integral and then afterwards you plug in the numbers. You might like option 2, the slick way, where you don't need to do the translating back. I'm integrating from 3 to 4 x squared over x cubed minus 8 dx. I'm going to do the same substitution, u equals x cubed minus 8. du is 3x squared dx. I see the x squared, I see the dx. I wish I had a 3, so I put in a 3 and pop out a 1/3 to cancel it. 3 is a constant, so I'm allowed to do that. My integral changes into an integral 1 over u du with a 1/3 out front. And now here's the key part. The new bounds of integration are not 3 to 4 anymore. It might be valuable if I'm doing a problem where I can see that this is where I'm headed. I may find myself writing x equals 3 to 4 to remind myself that these are x values. This 3 and 4 that they told us are telling me that x goes from 3 to 4. And if I do a substitution to change an integral from an x integral into a u integral, I need to change those into new u values. What are my new u values? Well, I have the way to convert x values into u values right here. X equals 3 and x equals 4 become u equals something and u equals something. When x is 3, u is 3 cubed minus 8 is 19. Okay, I remember doing that earlier. The bottom one was 3, so now the bottom u value is 19. The top u value was 4, so the top u value is, what's 4 cubed minus 8? That's 64 minus 8, that's 56. I like writing x equals here and u equals here. To remind myself that I have made the translation I'm supposed to write. And this equals, and now you keep going. Because I did the translating of the endpoints, I translated the bounds of integration, I never need to go back to x. Whatever number this integral is the number version of what this one was. If you weren't sure it was going to come out right, you can sort of go back and look what was going on along the way. I was going to end up with natural log 56 minus 19, because those are the u values that correspond with the x values. It's obvious how to check that this is right. 1/3 natural log absolute value u. I need to evaluate that from u equals 19 to u equals 56. 1/3 natural log absolute value 56 minus 1/3 natural log 19. I guess I don't need the absolute values because 56 is positive. And then maybe you do the same dumb thing. 56 over 19. And the reason I'm writing this in 2 columns is to emphasize, hey, look how much extra work this takes. You don't need to write. It's less writing total if I never have to translate back into the x's. But the key thing to emphasize is, if there are bounds of integration, you must change them. Like the option 3 the wrong way, and it's wrong, so it's not an option, is if you have the integral from 3 to 4 of, what was it, x squared over x cubed minus 3, 1/3, 3, 1/3 integral from 3 to 4 of 1 over u du. This is not correct. If you do the substitution with the bounds of integration, you must change the bounds of integration. This type of problem is maybe the reason that some teachers really hate you writing an integral where the x's and u's are mixed, because like if I have a bound of integration of 3 to 4 here, and there were x's and u's all mixed up in here, it's not clear whether you mean those to be x values or to be u values. And I can see that being like extra confusing. For me, the solution is we'll just call that x equals 3. And maybe now I'll get a chance to remember to change my x value to a u value or something. But in the end, you need to change the values of integration. I think it's valuable to write that as x equals 3 so that I have a chance to notice, ooh, I should have changed that to a u value. Yeah, substitution. So the moral of the story is, if you do a definite integral by substitution, then you must change the bounds of integration. Either don't use the bounds, do the whole integral, and then afterwards, whatever, or, yeah. I think you should know how to do. There's like two parts of all the tricks for integration we're going to learn. One is you need to have the idea of a good substitution. And we can do, how do you get good at having a good idea? You get good at having good ideas by practicing. Figuring out that u equals x cubed minus 8 is a good substitution to try requires this good idea having, and it's really hard to train yourself to be good at having good ideas. You can, and we're expecting you to, and the we is me. But it's kind of a different skill from just being able to perform a substitution. A skill I want you to have is it's good to be able to do a substitution even on a bad idea. Why? You're working over here but not over here? I wonder if the angle I'm holding the pen at is the real problem. It's good to be able to do a substitution, even if it's bad. Even if it's dumb. So like for example, black pen, exam. Black pen that still works. Why aren't you black? Example. Let's perform the substitution. U equals tangent x on the integral from 0 to 1 of x squared plus 1 over x squared plus 4 dx. Why would I want to use u equals tangent x? Well, I wouldn't, but the problem told me to. So I have to. This is a thing you need to be able to do. How do you make that happen? Well, a thing to know, usually when you're doing a substitution, you've got u equals tangent x, you take the derivative of both sides, and you pretend you're allowed to move the dx over to the other side. You get du is, what's the derivative of tangent? It is secant squared x dx. So if u is tangent x, then du should be secant squared x. For a normal substitution, where it was a good idea to do this, I would see a secant squared over here. And I don't see that. A thing that helps you able to do substitutions even when they're dumb, and this is useful to know even when it's not dumb, is that you can take this and solve it for x. If u is tangent x, then x is tangent inverse of u. Knowing that x is tangent inverse u is way more useful, because now I can change all these x's into something with u's. And knowing the derivative of tangent inverse, I can write that if x is tangent inverse u, then dx is the derivative of that, du. What's the derivative of tangent inverse u? It's 1 over u squared plus 1 du. And now, hey, I have a way to convert dx into u's too. Having written taking my u equals and changing it to an x equals very often makes even hard, crazy substitutions easy. My new integral is an integral of what's x squared plus 4 become? It becomes tangent inverse u squared plus 4. What's x squared plus 1 become? It becomes tangent inverse u squared plus 1. The 2 doesn't go into these exponents don't. This tangent inverse is not an exponent, so there's no rules of exponents to combine those or anything. What's dx? dx is 1 over u squared plus 1 du. And what do my bounds of integration become? X equals 0 becomes u equals, u is tangent x, tangent 0 is 0, tangent 1 is not easy, it's tangent 1, whatever that is. Hey, this number equals this number. These two things are specific numbers. If you know how to get your calculator to do a definite integral, and hey, that's a thing worth knowing. Do you have a calculator? Did your Cal 1 teachers let you use calculators? I'm not sure what the right thing to do is for this class. Yeah, these numbers are equal, and it's good to be able to do a conversion like that, even when it is not the most helpful conversion for doing a substitution. And you can do all sorts of halvesies. Halvesies is what my notes say. If I'm trying the substitution, u equals natural log of tangent of x, then the du rule would be du is, what's the derivative of natural log tangent x? It's 1 over tangent x times derivative of the inside. Derivative of tangent is secant squared x dx. If I wanted to try to solve this for x, I would take e to the both sides and get e to the u equals tangent x. And then tangent inverse both sides would give me x equals arctan or tangent inverse of e to the u. I don't know how you wrote it in your class. Some classes treat arctan and tangent inverse as different. For me, these are the same. These are two names for the same function. I don't care about the difference between them. It can be convenient to have different names for them to treat them differently. We're not going to treat them differently. Where did my music went? I bumped my volume button. This and this and this all describe the same relationship. If I know what u is, I can write down du is the derivative of that. If I know what x is, I can write down dx is the derivative of that. What's the derivative of arctan something? It's 1 over that squared plus 1 times the derivative of the inside is e to the u du. This and this are not obviously the same relationship, but they are the same relationship. And in fact, we can also do this halvesy version of the rule, where I don't have what x is and I don't have what u is. As long as it's u stuff on one side and x stuff on the other side, I can take the derivative of this with respect to u and get e to the u du equals, take the derivative of this with respect to x, secant squared x dx. And this is another rule that is the same as all three of these rules. Oh, I didn't write the dx. All of these are the same. The fact that these are the same is not at all obvious. Like, it helps to say, well, what's the relationship? If e to the u is tangent x, which it is according to all of these rules, then this becomes a tangent x. And if I moved this e to the u to the other side, it would become a 1 over e to the u, which would be a 1 over tangent x. So this part and this part match up the same. If I moved this to the other side, it would be e to the u squared plus 1. And since e to the u is tangent, that would be tangent squared plus 1. And hey, tangent squared plus 1 is secant squared. Like, it takes a little bit of work, but you can verify that these are the same thing. And they are the same thing, and it can be convenient to have either version of this rule. If I look at the last problem, if I was forced to only take these rules and figure out from that dx is 1 over u squared plus 1, that is no fun. You can do it. Dx is 1 over secant squared u du. How do I turn this into x's? Well, I need to remember the trig identity that secant squared is secant squared x. I would need to remember this trig identity that secant squared is tangent squared plus 1. The stylus is driving me nuts today. Tangent squared x plus 1 du. And now remember that tangent x is u, and that turns into u squared plus 1. Like, you can do that, but you'd way rather just know that you can do the derivative of both sides at other steps along the way. So far, this fact that you can find du or find dx has only been used in useless situations. Let's do one where it's more useful. Here's an example. let's do the integral of x squared. Oh, Jesus Christ. Come on, stylus. We need to... We're working. We're here. Okay. Let's do the integral of x squared minus 2x minus 3 all over the square root of 3x plus 1. I want to do this integral dx. We need to find a substitution to do. The best choice of a substitution is something that I see kind of stuck on the inside somewhere, whose derivative I see on the outside somewhere, or I see something like the derivative on the outside somewhere. The smart choice here is the fact that 3x plus 1 being inside the square root is kind of stuck in there. If I have a fraction, the stuff on top of the fraction I want to think of as outside. It's like touching the dx. I could pull it off the fraction if I wanted to. Whereas the stuff inside the fraction is the stuff that I can't. It's gross and not reachable. U equals 3x plus 1 is a good choice of u here. Or a good first choice of u that will turn out to work in a second. This is the hard thing about calculus is... Don't go off on that right now. They finish this example and then go off on that. We're going to do the substitution u equals 3x plus 1. Derivative of that is du is 3 dx. Or I can take that thing and solve it for x. If u is 3x plus 1, 3x is u minus 1, so x is 1/3 u minus 1. dx is 1/3 du. Okay, converting this to this is not super hard like it was in the last example, so doing this d version is not that valuable, but sometimes it is. Dx can become 1/3 du, and all of these x's, well, this 3x plus 1 can just become u, that's square root u here, and these x's that I don't know what to do with, like the best substitutions, there's no leftover x's. Sometimes there are leftover x's, and you just gotta suck it up and write out what those leftover x's are. They are each 1/3 u minus 1. This x squared becomes 1/3 u minus 1, all squared. This 2x becomes 2, 1/3 u minus 1. Was this a good substitution? Get in the habit, after you've done a substitution, of checking, have I made the problem harder? You're going to try things in calculus that turn out to be a bad idea. You want to give yourself a chance to notice, hey, wait, that was a bad idea. I should go back and try something different. I have u to the 1/2 on bottom. I've turned my problem from something that had a kind of gross bottom to a much simpler bottom, but the fairly simple top has become way grosser. Like, this new top is way more complicated. But wait, you need to be able to stop and say, this is all stuff that looks gross, but I can FOIL all that out. The top was a quadratic polynomial, and it's still a quadratic polynomial. It'll be work to make it look like a quadratic polynomial, but I know how to do that work. 1/3 u minus 1 squared, well, 1/3 squared is 1/9. U minus 1 squared is... Why? Oh, yeah, recover the note. Maybe the problem isn't my stylus. Maybe the problem is this software sucks. du is 3 dx. Oh, this is where I was when the stylus started freaking out. I bet that's what it is. X was 1/3 u minus 1. Dx is 1/3 du. Using these rules on this dx and this x and this x, and use this rule on this 3x plus 1. I had u to the 1/2 on bottom. I had 1/3 u minus 1 squared minus 2 times 1/3 u minus 1 minus 3. Dx becomes 1/3 du. Let's go ahead and pull the 1/3 all the way out. What is this? I get 1/3 1/3 squared is 1/9. Jesus Christ. Come on, stylus. 1/9. U squared minus 2u plus 1 is what you get when you FOIL out that squared. Minus 2/3 of u minus 1 minus 3 all over u to the 1/2. I might be tempted to take a common denominator on the top, and that'll work. I like knowing this trick of if you multiply the, like when you have fractions inside of fractions, it's nice to multiply the top and bottom of the big fraction by the least common denominator of the little fractions. Here, if I multiply the top and bottom of the big fraction by 9, that'll get rid of the little fractions on top, and that's all I need. I'll get 1/3 integral of, I get 9u to the 1/2 down here. 9 times this gives me u squared minus 2u plus 1. 2/3 of 9 is 6 u minus 1s. Minus 9 times 3 is 27. This 9 on bottom is a constant of 1/9 I can pull out of the fraction. 1/9 and 1/3 will make 1/27 outside. I got u to the 1/2 on bottom. And on top I have u squared minus 2u minus 6u will be minus 8u. Plus 1 plus 6 is 7. Minus 27 is minus 20. All right. If you had a teacher in high school who made you spend all year factoring, which there's a good chance you did, and I guess that's a separate rant about how dumb it is that high school teachers make you learn how to factor everything forever. You might be trying to factor the top. Factoring the top is not helpful. The thing to know is, like, it's hard to remember how smart Cal 2 students are. I assume you're aware that if you have a fraction that splits into separate fractions, you can't do that with a bottom. A over b plus c does not equal a over b plus a over c. Usually you're doing it this way because you found a common denominator so you can add the fractions, but it also works this way. And the fact that it works this way is the reason why you would prefer to have a simple thing on bottom of a fraction, even if it makes the top messier. Because when you have a simple thing on bottom of a fraction, like we have here, you can split that up into separate fractions. I got 1/27th integral of u squared over u to the 1/2 minus 8u over u to the 1/2 minus 20 times 1 over u to the 1/2. Each of these things is now just a power of u. I get 1 over 27 of, still not integrating yet, the integral of u to the 2 minus 1/2 is 3/2, minus 8u to the 1/2, minus 20u to the negative 1/2. And now I'm ready to use the power rule. I get 1 over 27 of 3/2 plus 1 is 5/2. Reciprocal of that out front is 2/5. 1/2 plus 1 is 3/2. Reciprocal of that up front is 2/3 times 8 is 16/3. Negative 1/2 plus 1 is positive 1/2. Reciprocal of that out front is 2 times 20 is 40. Here's an answer, but it's written in terms of u's. I want something written in terms of x's. My answer in terms of x's is 1/27th of, what was u? U was 3x plus 1. So I need 2/5 3x plus 1 to the 5/2 minus 16/3 of 3x plus 1 to the 3/2 minus 40 times 3x plus 1 to the 1/2 plus c. Maybe you should push the 1/27th in. It feels weird to have some gross, like factor out some of the fractions but not all the constants. I don't know. It's hard to know what the cleanest way of writing this answer is, but here's a correct answer. A lot of places in math, like for lots of these integration problems, I feel like you get a lot smarter by taking your answer and taking the derivative and seeing how the derivative turns out to be the original problem. I don't know if this is one of those problems. I think in general, you should try to have a curiosity about how on earth does the derivative of that turn out to be this? And I think doing that a bunch of times is good. This one, not clear. Not clear at all. If you do it, let me know. I'm excited to see how it, when you take the derivative, there's going to be some crazy simplification necessary to turn it into the original. Anyway, that's what I wanted to say about substitution. In theory, substitution should be a thing that you covered in Cal 1. I'm hitting some of these details because I don't know if you covered what to do when the little numbers are there, or like there's some little things that I think are useful for you to see and learn that you might not have seen in your Cal 1, but that's substitution. Oh, that's the end of me telling you to do substitution problems. I still have the homework up. What's the homework look like? That's everything you need to do 1 through 4. Go do homework number 1 through 4. I might add some more problems. I want there to be a problem. I might get... Yeah, I didn't put one about do the substitution even if it's a dumb idea. Is that somewhere later on? Yeah, crud. I was hoping to not add problems this year, but I guess I'm doing that. Don't worry too hard. I guess, yeah, I can be smart. I'll add problems and label them 4A, 4B, 4C so the numbering doesn't change. Oh, hey, by the way, like, people get strung up about, do I have to do these? I'm going to add extra problems. If you print off this homework sheet and just do these problems, that's fine. I'm adding the problems for your benefit. Like, I do not care about this homework grade. I have to make the homework be graded because otherwise you won't do it, but I don't care about the homework too much. If there's a problem that wasn't on the version of the homework sheet you did and you didn't do that one, I'm never going to take points off. But hey, you should probably do that. Hey, maybe your Cal 1 teacher didn't talk about what sign with an H is. Let's talk about that real quick. There's these functions. SINH is pronounced cinch when you say it out loud. And it's the hyperbolic sine function. And its formula is, it's sinh of x is e to the x minus e to the negative x over 2. What? That's a weird function to give a name to. It turns out it's useful. Damn it. Divided by 2. And cosh of x, pronounced cosh, is hyperbolic cosine, and it's e to the x plus e to the negative x over 2. You should know these functions, or I'm going to expect you to know these functions. I don't know if you should know them before now, but the calculus book I taught from uses these functions in it, so I'm going to be using them. Why do these things have special names? The reason these things have special names is they kind of act like sine and cosine. You know how sine is an odd function? It's got rotational symmetry. The thing on the right is the opposite of the thing on the left. Sine of negative x is negative sine x, and cosine of negative x. So sine has rotational symmetry. If I spin this picture 180 degrees, that lands back on itself. Cosine has left-right symmetry, meaning cosine negative x is just cosine x. It's an even function. It turns out to be a fact that every function can be written as something even, the sum of an even function and an odd function. And the way to do that is you write f of x as f of x plus f of negative x over 2 plus f of x minus f of negative x over 2. This is always going to be an even function. This is always going to be an odd function. Sinh and cosh, this is an odd function. Sinh of negative x is negative sinh x. Cosh is an even function. These are the even and odd functions with the property that when you add them up, you get e to the x. This is one of the fundamental identities of sinh and cosh. Sinh plus cosh equals e to the x. Sinh is an odd function. Sinh negative x is negative sinh x. Cosh negative x is cosh x. Cosh eats up a negative sign. Sinh poops out a negative sign. These three properties are enough to be the definition of sinh and cosh. The reason they get the names sinh and cosh, like why are they like sine and cosine? Look at the formula for sinh x, and let's undo that. Sinh x is e to the x minus e to the negative x over 2. What's the derivative of sinh? Well, this is 1/2 of the over 2 is a constant out front. I can leave that out front. Derivative of e to the x is e to the x, minus derivative of e to the negative x is e to the negative x times negative 1. That makes this a plus. Hey, that's cosh. What was cosh? Cosh was 1/2 e to the x plus e to the negative x. The derivative of cosh is 1/2 of derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x, but with a minus sign. It's sinh. Sinh and cosh are each other's derivatives. It's the way that sine and cosine are almost each other's derivatives, but sine and cosine, if it was a cosine, there would be an I out here. There isn't for sinh and cosh. And this makes all sorts of goofy things kind of like the e to the x rules. So yeah, there's a function tanh that is defined to be sinh over cosh. There's a function sich. It's defined to be 1 over cosh. There's a function coth, hyperbolic cotangent, it would be cosine over sine, now it's cosh over sinh. There's a function cosich, is 1 over sinh. It can be worth figuring out what these derivatives are. Most people don't have these ones memorized. They are very similar to the regular trig derivatives, but the minus signs show up in different places. Getting them to simplify, I guess there's one more important identity that I want you to know for sinh and cosh, and it's the Pythagorean identity. You know sine squared plus cosine squared is 1, right? let's say we didn't know what sine squared plus cosine squared was. If I take the derivative of both sides, what's the derivative of sine squared plus cosine squared? The derivative of sine squared plus cosine squared is, derivative of this is 2 something squared, power rule, 2 comes out front, times the derivative of the inside. What's the derivative of this? Power rule, the 2 comes out front, derivative of the inside. Hey, these are the same thing, but with a minus sign, it's 0. Sine squared plus cosine squared is something whose derivative is 0. So sine squared plus cosine squared is a constant. What constant number is it? Well, I can take sine squared plus cosine squared of 0. That's an easy number to plug in. It's 1. If it's constant and it equals 1 at one point, then it must be 1 always. I can use that same trick to figure out what's going on with sinh and cosh and get a similar identity. But the version for cosh and sinh is, they usually write it cosh squared minus sinh squared. If I take the derivative of this with respect to x, I guess I won't write it out because it's the exact same. I get 2 cosh sinh minus 2 sinh cosh. This minus sign isn't here, but it is here, and that's going to be the thing that causes it to be zero. So cosh squared minus sinh squared is a constant, and the constant turns out to be 1. If you plug 1 into cosh, you get, if you plug 0 into these functions, you get 1 and 0. Cosh of 0 is 1, sinh of 0 is 0. Jesus, I am having so much problems here. So cosh squared x minus sinh squared x is some constant, and the constant turns out to be 1. Sinh and cosh also behave like sine and cosine in that cosh of 0 is 1, and sinh of 0 is 0. Same way sine 0 is 0, cosine 0 is 1. These functions are super useful in differential equations. There's a nice thing you can do with sine and cosine to write your answers out that you can't do with e to the x and e to the negative x, and you kind of wish e to the x and e to the negative x would act more like sine and cosine, and it turns out these are the ways to manipulate e to the x and e to the negative x to turn them into sine and cosine. And anyway, the things you need to know are the derivative of sinh and cosh are each other, and let me put it all in a box. No. You should know the formulas for sinh and cosh. The derivative of sinh and cosh are each other. And it's useful to know the Pythagorean identity for them. Cosh squared minus sinh squared is 1. Cool. Okay, that's what I wanted you to know about substitution, plus this random other sinh cosh fact that you don't particularly need to know, but well, you need to know a little bit about sinh and cosh if you didn't already. Let's move on to our next big topic. Our next big topic is integration by parts. In the world of mathematics, like by the world of mathematics, I mean of mathematicians doing math at the professional, at the research level, like when research mathematicians talk about integration by parts, it always shows up as this surprisingly useful thing. Like, we got this, and now what do? We do integration by parts. What? Oh my god, I can't believe that thing turned out to be useful in this crazy context. Integration by parts turns out to be useful in lots of crazy contexts. Like advanced contexts, I mean. The way, and It's useful for doing integrals, by the way, is the original context, is the one you're about to see. It helps you do integrals. If substitution is the chain rule backwards, if I took a derivative using a chain rule, and now I want to take the integral of that, probably I'm doing a substitution, is the version of integrals that fixes a derivative that needs the chain rule leads to an integral that needs integration by substitution, like that relationship. God, I can't make a goddamn sentence today. Let's try this. Chain rule is to substitution as product rule is to parts. If you use the product rule to take the derivative, then parts will probably be the thing you need to do to take an integral. Integration by parts is the integral version of the product rule. It is the product rule backwards. Let's start by remembering the product rule. The product rule says that the derivative of u times v is derivative of the first, leave the second alone, minus leave the first alone, derivative of the second. If you do this or plus, it's a plus. Minus is the quotient rule. We're not doing the quotient rule. That means, so if the derivative of this is that, then the integral of that, du dx times v, plus u times dv dx, dx must equal u times v. Well, it turns out this version of the integral by parts rule is way too specific to be useful. If you're going to look at a problem and like having this and this plus this and this, having all four of those things being lined up in exactly the right way so that you know the answer is just asking for a miracle to happen. That is not useful. And the thing that you end up doing if you try to use this rule is when you say, well, I have this, and I wish I had this. I'm going to put this here, and then subtract it off, and now I know the integral of this, and I want to know the integral of the other, so you figure out the other integral. The thing you end up doing is you always have one of these, and you want the other. So the way we write down the integral by parts formula is we move one of these to the other side of the formula. That says the integral of du dx v dx plus, like I can split an integral across a plus, this is a rule, equals u times v. We move one of these to the other side, and the traditional one to move over is this one. The integral of u times dv dx equals uv minus the integral of, I'm going to switch the order here, v times du dx. And traditionally, we cancel these dx's as if the d thing was a fraction, which it's not, and this doesn't make sense, but it sort of adds up to using u and dv. We're sort of doing the same type of thing we do when we do a substitution, when we pretend this is it. This is the usual way people write the integral by parts formula. Put a box around this. You're gonna be referencing this a lot when you do integral by parts problems. Let me show you the most bog standard type of integral by parts you can do. We're going to do the integral of x e to the x dx. And I want to do this by parts. The parts formula has a u and a v. We want to know what are u and what are v. And I want to know what are dv and du, and they have the same relationship that u and du had when I was doing substitution. And a lot of people, I've seen some modern teachers like not using the letter u in their parts because they don't want people to get mixed up. I feel like I might be too old to change at this point, but we need to know what's a u and what's v and what's du and what's dv. And it feels like we've got two decisions to make. What's u and what's dv? But really this is one decision, because for this formula to be useful, this integral, u dv, must be this integral. The integral of x e to the x dx is going to be the integral of u dv. So once I've decided what u is, let's say I picked u as e to the x, dv must be everything else. There's really only one decision we're making. When we pick something to be u, dv is automatically everything else we see in the integral, because this thing must be the integral of u dv. The fact that we're using parts on the integral forces everything else to line up. Okay, I need to choose a u. What is my u? I'm going to make the choice of e to the x. If u is e to the x, then dv is everything else. The e to the x has been taken by being u, so dv must be everything else in the integral. dv must be x dx. Just like when we do a substitution, I'm going to scroll up to a random substitution we did a while ago. When we write dx, dx is some stuff, du. Same thing's happening with these u's and v's. U should be something that doesn't have a dx or a du on it. dv should be something that does have a dx on it. Keeping these straight fixes this up. Just like with substitution, to find what du is, I take the derivative of this. If u is e to the x, du is derivative of that dx. Derivative of e to the x is e to the x. So du is e to the x dx. The in-between step that we're not usually writing here. Come on, stylus. You got the dot. The in-between step might be that du dx is e to the x. Multiply both sides by dx. I'm not going to write that out much, but that's why I need to have the d there. I might be thinking to myself that if I have dv equals x dx, then, come on, then dv dx equals x. I need to figure out a choice of v whose derivative is x. V is going to be the integral of x dx. I don't usually write the integral symbol here, but this is what we're doing, is we need to do a tiny little integral in our heads right now. This is the first place where your integral by parts can fail. Like very often, I decide I'm going to try integral by parts. I'm going to let u equal this, so du is this, so dv is that, so v is, oh crap, I don't know how to do that integral. Or maybe just, I don't know how to do that integral right now in my head as the tiny step of a bigger problem. In general, the amount of writing we do is just this much. dv equals x dx, and now I'm thinking, what's the integral of x dx? That's what I write here as v. You want this to be something you can do right now in your head. If you're starting an integral by parts and this little tiny step takes 3 pages to do, there's a good chance there was a better way of writing it. If it works, it works. If you have something that works, go for it. But probably you want this to be a tiny integral that you can do right away in your head. What's the integral of x? It's half x squared. It's actually half x squared plus c, and I'm allowed to put a plus c there if I want. Usually you don't want to. It's really hard to come up with an example where you would want to put a plus 3 there. Like, I would want to put the plus 3 there if it's immediately going to cancel with something else. That's like an advanced version of the trick. You're allowed to put a plus a constant there, but most of the time you don't want to. And now, let's see what we got. So, good news, we were able to find v. This is a step that could have failed and we could have had to try something else. The integral by parts formula says the integral of u dv, which is this, u dv is e to the x dx, good, equals, the right-hand side is uv. What is u times v? It's e to the x times a half x squared, minus the integral of v, half x squared, du, e to the x dx. We did an integral by parts. Just like with substitution, parts is a technique that doesn't solve your integral, it turns your integral into another integral. So we used to need to know how to do this, now we just need to know how to do this. This first thing is half x squared e to the x. Usually write the simpler functions first, minus the half can come out. Integral of x squared e to the x dx. Just like with substitution, it's good to get in the habit of taking a minute to say, okay, have I made the problem better? The best possible situation is I know how to do this integral and I'm done. Do it, you're done. If you don't know how to do it right away, at least hopefully you've turned a difficult integral into a simpler integral. Is this easier? No, that's not easier. That's worse. Like I know the integral of e to the x, but the x is what's making it hard. And now there's two x's? That's like even worse. Oh, crud. Yuck. Even worse. Gah. So, if you're in an exam and you do this type of thing, I see a lot of students who just go, scroll, this is all wrong. Don't do that. There's a good chance you did some work there that I can give you some points for, or at least some work that you can come back to later. Do cross it off so that I know this wasn't part of your solution, but do this. Do like one big gentle X to say, this was all wrong, but you can totally read it if you need to come back and look at this later. Maybe you try something else and that doesn't work and you wish you had this. Or maybe you just want me to be able to see this is a thing you tried. These problems aren't things that you look at and you know how to do. I don't know if your Cal 1 teacher told this to you. Derivatives are algorithmic. If you can write down a function, like sine of e to the x over cosine x, whatever, the rules of differentiation are a complete algorithm. If you know the quotient rule and you know the derivatives of all the functions, you can write down the derivative of any function. And it works. Integrals are not that way. There's simple integrals, for example, integral of e to the x squared. The integral exists. There is some function whose derivative is e to the x squared, but I can't write down a formula for that function. Or if I can, it's going to be using new names. There's an easy way of demonstrating that. What's the integral of 1 over x dx? It's natural log x. The only reason you're able to do the integral of 1 over x is that natural log is one of the functions we've decided is so important that it gets its name. This function didn't get a name, or at least it didn't get one at the high school level. If you go to a stats class, they give names to this function. But in general, every derivative is doable, every integral is not necessarily doable. This is one of them. The integral of cosine squared is not something you can write a closed form expression for, the integral of all these things. This is sort of, the fact that you can't write down a formula for the answer can be misleading into thinking that integrals are harder than derivatives. In the theoretical sense, it is much easier for an integral to exist than a derivative. Like, you've seen how, I hope you've seen that absolute value x is not differentiable at 0. The function has no derivative at this point. There's no tangent line. The idea of taking the derivative here doesn't exist. It is, in general, much easier for a function to have an antiderivative than it is for it to have a derivative. Absolute value x doesn't have a derivative everywhere, but it does have an antiderivative everywhere. In the theoretical sense, integrals are way easier. You're just less likely to be able to write a formula down for it. The fact that it's not algorithmic, for a derivative, if you learn all the rules, you can always do every derivative. Integrals are not like that. Integrals, this procedure we're learning for exam 1, is some tricks that sometimes work. And you're going to be responsible for being good enough at these tricks to use them when they work. But generally, you should be aware going in, there's kind of a ruse going on. All the integrals I'm handing you, just coincidentally, are things where the tricks work. And it's kind of a fake out. I remember I felt similarly betrayed when I found out that, like, did you ever have an algebra class where you're trying to factor? You can definitely factor x cubed minus 8x minus 8, because if you can't factor it, you can use the quadratic formula and get that it equals x minus something, x minus something. Like, this trick about taking polynomials and factoring them. Maybe someday you had to do x cubed minus x minus 8. You're using the rational root theorem, and you're doing synthetic division, and you're listing all the things that could be roots, and you found, ooh, this one worked, and now I have this left. And they gave you giant polynomials and said factor this all the way down. And I learned the tricks they gave me, and I was able to do the problems they gave me. And then I got to grad school and found out once you get up to degree 5, the tricks don't work necessarily. There's this thing called the insolvability of the quintic. For most 5th degree polynomials, you cannot write down a formula for the solutions of that polynomial. The solutions exist, but there is a quadratic formula, there is a cubic formula, there is a quartic formula, there is not a quintic formula, and there cannot be. Some problems cannot be solved, at least even though the solutions exist theoretically. You can't write down what the solutions are using square roots and cube roots and whatever. We're in the same situation now with integrals. Many integrals are not doable. The thing you are doing then is getting good at trying tricks and seeing if they work. Here we tried doing parts once, and it didn't work. And you need to not get discouraged when the first thing you tried doesn't work. And you need to not treat this like garbage. This was a step in trying things. And very often on the exam, if you have a problem that you tried 3 different things on and none of them worked, I can probably find a way to give you a bunch of points for that. Don't feel like getting the answer is 100% of the problem, but you got to do enough problems that you're good at figuring out when the tricks work. Okay, I went on that longer than I meant to. Let's actually do an integral by parts. We're going to do that problem. The integral by parts formula is the integral of u dv is uv minus integral v du. I want to say what's u and what's dv. From those, I'm going to say what du is, and I'm going to say what v is. It turns out I had them in the wrong order. It turns out u equals x is a pretty good choice of u, because the derivative of x is 1, isn't really there anymore. X is a nice choice of u because it goes away when you take its derivative. The new integral I'm going to have won't have u, it's going to have du, which means it has less stuff on it. U is often a very good choice for your... X is often a very good choice for your u because it goes away in parts. X is never a good choice for a substitution of u. Why is that? Okay, if u is x, dv needs to be everything else. This was u, so this stuff is dv. dv is going to be e to the x dx. Can I find v? Can I find the integral of e to the x? I sure can. It's e to the x. So what does this get? The integral of x e to the x equals uv minus integral v du. uv is x e to the x minus the integral of v is e to the x, du is just dx. I don't need to write the 1. It looks like it says 6. If you haven't noticed that, you should notice that. I have x e to the x minus, what's the integral of e to the x? It is e to the x plus c. That's the integral of x e to the x. Parts worked here. When it works, so parts I think is one of the best places to learn what... You will understand parts more deeply if many times you check your answer by taking the derivative. I'm going to check this by differentiating this. What's the derivative of x e to the x? That's a product. I have to use the product rule. I shouldn't be surprised that I have to use the product rule after I did parts. Derivative of x is 1 times leave the second part alone plus leave the first part alone. Derivative of e to the x is e to the x. Minus, now what's the derivative of this? The derivative of this is e to the x. Plus what's the derivative of a constant? It's 0. The derivative of this was this stuff. X e to the x, that's the thing I wanted, but wait, I don't want this 1 e to the x. Well, good thing there's an e to the x there to cancel it. This is a thing that spits out the thing I wanted from my answer, but it also spits out some extra garbage. The second integral is you figuring out what you need to put there to cancel the extra garbage that the product rule is going to give you. That's how the product rule flows. Like that's the general pattern going on. Let's do some more examples of this. Hey, heads up. If you didn't know it, hey, what's the integral of e to the 4x? Maybe you can do this by a substitution. The substitution u equals 4x works, but you probably want to be able to do this integral in your head pretty soon, if not right away. The integral of e to the something is e to the something. When I take the derivative, it's going to poop out an extra 4 from the chain rule. Putting a 1/4 cancels that. You want to be able to do an integral like that in your head. In general, if you know the integral of something is something, then sticking a constant on the inside only changes the integral by needing to divide by that constant. And it also works if you have a linear function inside. If you're scooting it by a constant, you might like to know that the integral of that is, I guess there's plus c's on the right side of all these. In general, you want to be able to do things like that. So for example, the integral of cosine of 5x minus 8. What's the integral of cosine? It's sine. So the integral of cosine 5x minus 8 is going to be sine 5x minus 8 with a 1/5 out front. It's really good to be able to do steps like this in one step in your head. If you weren't sure of it, you can do the substitution u equals 5x minus 8. But very quickly in this course, you're going to get to a place where you want to be able to do this baby kind of substitution all in one step. It shows up in awkward places too. What's the integral of the square root of 5x minus 1? Well, I know the integral of square root x. It's x to the 1/2, so its integral is x to the 3/2 with a 2/3 out front. Well, the 5x minus 1 can hang out there as long as I put a 1/5 to cancel it. It's good to be able to do integrals like this in your head. Maybe not always with the minus 8, but without it for certainly. Let's try an example of an integral by parts. For a lecture on integration by parts, I haven't done enough integrals by parts. Example. Let's do the integral of x squared sine 5x. We're going to do parts. The parts rule is the integral of u dv is uv minus the integral of v du. I need to pick my u, I need to pick my dv. There's only one picking happening there. I pick my u and then my dv is everything else. Last time I learned that u equals x is a good choice because x goes away when I take its derivative. In this setup, I don't have an x, I have an x squared, but that's kind of like an x. When I take its derivative, it doesn't go all the way away, but it does get cleaner. The derivative of x squared is 2x dx. There's less x's. That seems like progress, if not a complete solution. What's dv? Dv's got to be everything else. It's going to be sine 5x dx. So u is x squared, du is 2x dx. dv is sine 5x. V is going to be the integral of sine 5x. What's the integral of sine? Derivative of sine is cosine. Integral of sine is negative cosine 5x. But the 5 means I have to divide by 5. Negative 1/5 cosine 5x is going to be my v. Let's use the parts formula. The integral of u dv equals u v minus the integral of v. Actually, let's let these minuses cancel right now. v 1/5 cosine 5x du plus, if I pull all these constants out, it'll be 2/5. Usually I want to pull that outside of the integral. I'm going to leave it right inside the integral this time for a good reason that you will see in a second. Alright, I still need to do this integral. This integral is going to take several steps. I'm going to get very sick of writing the same function over and over. I'm going to write blah, blah, blah plus, blah, blah, blah plus, and I'll come back and fill it in at the end. I think everybody does this to some extent, but I do it in maybe an extra sloppy way. You do what you need to do to keep your work organized, but there's a lot of work that's going to be done here with a lot of negative 1/5 x squared cosine 5x out front. How do I do this integral now? I guess first step, have we made progress? Is this an easier problem than the original one was? There's a 2/5 there that wasn't there before, so that's worse, but not really worse. I can deal with a constant out front. That's not a big deal. The sine turned into a cosine. Is cosine worse than sine? No, those are equal difficulty. Every time I learned how to do something about cosine, I learned it about sine at the same time, so that's not worse. The x squared turned into an x. Aha, we have made progress. We used to have something with two x's in it, and now we have something with only one x. It is one step simpler than it used to be. Am I ready to do the problem? No, I don't know this integral right away off the top of my head. How can I do this problem? Well, I just saw how integrating by parts changed an x squared into just an x. There used to be two x's, now there's one less x. It was one step simpler. If integrating by parts makes it one step simpler, we went from two x's to one x. Ideally, I'd like to have 0 x's there. So let's try integrating by parts again. When I'm doing integral by parts again, it is really nice not to have stuff outside of the integral, and also not to have a minus. I'd like to have a plus here, and I'd like to not have a minus here, because I don't want to have to remember to put all this stuff in parentheses. The integral by parts is going to give me more stuff. If I have a minus here, then I have to remember that the minus goes through the parentheses. If I have the 2/5 outside the integral, I'd have to remember the 2/5 hits the all of this part of the integral by parts stuff. So I think it is way better if you have any constants here, including a negative, to push them inside and group them in as part of the x's or whatever. Last time I let u be x squared. This time I'm going to keep going in the same direction and let u be this x. So dv is everything else is 2/5 cosine 5x dx. The 2/5 I left inside the integral sign is now part of the dv. It's going to be hanging around the whole time. I like having it inside here so I don't have to deal with distributing it elsewhere. Du is derivative of that is 1 dx. V is the integral of this. Integral of cosine is sine, but I gotta divide by 5, so the 2/5 becomes 2/25. I can put a plus c, I don't usually want to, I don't see any reason to this time. There. So this now equals the first stuff, plus I want uv minus integral v du. That's u is x. V is 2/25 sine 5x. I'm not writing them in that order. I'm writing them in the normal, prettiest order to put them in. I don't want to view the updates. Minus the integral of v, 2/25 sine 5x, du is just dx. Hey, I can do this integral. I know the integral of sine. The integral of sine is negative cosine. Gotta divide by 5. 2/25 becomes 2/125. Plus c. And this thing is still here. And this thing is still here. And here's the answer. And again, I think it makes you... So this is an example where we did parts twice. If I check my answer by taking the derivative and seeing that it equals the thing it was supposed to equal, let's do that. This needs the product rule. Derivative of this is negative 1/5. Derivative of x squared is 2x, so that gives me 2/5 x times, leave the second part alone, cosine 5x, plus leave the first part alone, negative 1/5 x squared. Derivative of the second is negative sine 5x times 5, plus now I need the derivative of this, is also a product rule. Derivative of 2/25 x is 2/25. Leave the second part alone, plus leave the first part alone, 2/25 x times derivative of sine is cosine 5x times 5, plus derivative of 2 over 125 cosine 5x is derivative of cosine is negative sine 5x times derivative of the inside is 5. This is the derivative of that mess. The derivative was supposed to be, what was our original problem? X squared sine 5x? Does this whole thing equal x squared sine 5x? Aha! There's a 5 and a 1/5 leaves me x squared sine 5x. That's the answer. Here I have negative 2/5 x cosine 5x. Here I have positive 2 over 25. 5 cancels with that. Gives me 2/5 x cosine 5x. Cancel, cancel. This thing, 2 over 25 sine 5x. Negative 5 and 125 leaves 25. Negative 2 over 25 sine 5x. This cancels with this. Doing the product rule on that gave me the thing I want and some garbage I don't. Doing the product rule on that gave me the thing I needed to cancel with that garbage, but also a new piece of garbage. Derivative of this cancels the last piece of garbage. So the thing we want is there, and everything else canceled off a little bit at a time. This is integration by parts. It's rough, and it involves coming up with a good choice of u. Very often there are lots of u's you can choose, and one is a good one and one is not a good one, and we're going to do more examples of that tomorrow. I'm going to plan on streaming about 4 every day. Actually, why don't we, let's say we'll start at 4:15 is the plan. I'll turn the stream on closer to 4. I've been streaming to I'm also teaching Math 122 right now. I stream to them before you guys. So if you show up early, you can see me do some business calculus if you felt like that. You guys have any questions? I haven't seen anything from, the only things I've seen got texted to me are that people are here. Okay. Oh, so homework. You have everything you need to do the substitution stuff, and maybe the first few parts ones you can start trying out. There's some hard stuff in there sooner. We'll do some examples of harder parts next time, and we'll keep going. Hooray! I'll see you guys tomorrow, or, whenever you watch the video. Try and get started on the homework. It's not going to be due until exam day. I'm not going to be real strict about do this by this day and that by that day. You need to get it all done by the exam. Don't wait until the last minute to do it by the exam. Doing it sooner lets you ask questions. If you have questions you want me to do in lecture, send them to me before 4. If it's something simple, I might answer it right away by text. Yeah. See ya. Now, where do I turn off the live stream? End stream. End.